Okay, let's get started. So today we're very lucky to be joined by Professor Mike Fall for today's Thursday seminar. Mike is currently adjunct professor at Johns Hopkins University, having recently retired from a long career at Space Telescope Science Institute. Mike has had a research career which has spanned over 50 years, and he's done many very influential things in this field across a broad range of astrophysical topics. So, for instance, back with George Asapnew in the 1980s, he understood how disk galaxies form in a cosmological context. He worked on the mass function of globular clusters and how they're tidally stripped in light-free galaxies. He worked on the dust absorption in external galaxies by interstellar starlight. These days, as we heard at the Bacall lunch the other day, he's working on some very nice stuff on the heating of galaxies, spurious heating of galaxies in cosmological simulations. And today he's going to tell us about something that he has been working on for, I think, about 40 years, more or less, on and off, which is to do with galaxy scaling relations. We're going to have a new look at them. So please welcome Mike Fall.
Oh, well, friends. Galaxies are complicated objects, and the more we study them, the more complicated they seem. But beneath that complexity, they're the main properties of the most fundamental basic properties of galaxies, like their mass, their energy, and their angular momentum, are based on very simple scaling relations. And I kind of think of these as sort of the fundamental description of galaxies, or at least one of the most fundamental descriptions, in the same sense that the most fundamental description, say, of turbulent flow comes from looking at the energy spectrum of the eddies in the turbulence rather than the particular features of individual eddies. And so this has also, I think, provided one of the clearest, most transparent windows into galaxy formation. And that's the story I'm going to tell today. But before we get into the specifics of that, I just want to mention that the talk I'm going to give today is based on results from about a half dozen papers done over the last few years. This is a resurgent interest of mine. I left the area of astrophysics for a long time, but I've come back to it recently. And here are my collaborators, Aaron Romanovsky, Enrico De Teodoro, Lorenzo Posti, Patrick Ogle, Vincent Rodriguez Gomez, and a few other people. But these are the main ones. And so I'm going to present the highlights of about a half dozen papers made in collaboration with these colleagues. And in order to fit this all into an hour, I'm going to basically give you just the highlights. There isn't going to be time for me to go into as much technical detail as I would. I mean, each one of these projects could be probably a seminar on its own, but I'm going to focus on the highlights because I think that helps us see the big picture. I'm happy to talk about the technical details with anyone who wants to, but I'm going to try and skim over those as much as I can this hour. So let's leave the really technical questions maybe to the end of the talk. But if there's anything that requires clarifications, I go along, please interrupt and let me know about it. Okay, so here's the first and maybe the most famous scaling relation for disk galaxies anyway. This is the relationship, the Tully-Fisher relation, the relationship between the luminosity of a galaxy on the vertical axis and the width of the 21 centimeter signal, which characterizes how rapidly the galaxy is rotating. And this is the discovery diagram here. You see there's a fairly tight relation between these two quantities, relating essentially the amount of stars in the galaxy to how fast it's rotating. And at the time, they thought the power law index of this relation was between 2 and 3. Now, here's a much more modern version of this diagram. This is probably one of the best ones that's out there now, with the best selected sample. And this, now in this modern representation, is to plot the mass and stars of the galaxy to estimate the mass to light ratio from the colors and that sort of thing, convert a luminosity to a mass, and then plot it versus the velocity on the flat part of the rotation curve, which one gets from the rotation from a 2D velocity map of the galaxy. And what you can see here is this very tight relation. And now the slope comes up to be about 4. This is the standard slope, and that's been fairly stable now many, many years.
Type relation allows for 2 orders of magnitude deviation of some of the points.
Yeah, no, I can't remember exactly. The open ones are less confident. I can't remember the reason for that right now. But most of them do lie on the spheroid type relation. 2 orders of magnitude, maybe 1 order of magnitude. Anyway, I think there are two immediate consequences of this for galaxy formation. This relation, by the way, has been mainly used as a distance indicator. The velocity here is independent distance, whereas the luminosity does depend on distance. So if you see a galaxy and make these measurements, then you think it lies on that relation, then that gives you the distance of the galaxy. And so there have been hundreds of papers written about it from that aspect. Not so many actually in terms of its implication for galaxy formation, but there are 2 immediate consequences, implications for galaxy formation. I think one is that it tells you immediately how much energy the galaxy had to radiate away to get into the state that it's in today. And the other is, I was about to say, except maybe I shouldn't now that Bruce made that rude comment, that somehow the galaxy knows to make an amount of stars that's very sensitive to the overall depth of the potential of the galaxy. That's a remarkable result, I think, because we usually think of star formation processes as being something fairly local, but the rotation velocity of the galaxy is determined by the depth of the potential well, which is a sort of more global property of the galaxy. Okay. The next one I want to talk about is this one I found actually a long time ago, and that's the relation between the angular momentum per unit mass in the galaxy, in the stellar component of the galaxy, and the mass of stars in the galaxy. And what you see here is that the disk galaxies, the disk-dominated galaxies, lie on a line here with a slope of about 0.6. It's a nice power law, fairly tight. And then elliptical galaxies are roughly an order of magnitude below that on a sequence that's kind of parallel, more scattered because we don't know the orientations of the elliptical galaxies as well. Look at this diagram just as these types of measurements were first becoming available. So, this diagram would not have been possible a year or 2 before that. But anyway, that has some interesting implications for galaxy formation, which we'll get into. Now, here's a more recent version of this. My conjecture was that the gap between the ellipticals and the spirals would be filled in by galaxies of intermediate types. And then that was tested in this paper I did with Aaron Romanovsky many years later. So what's plotted here, again, is the log of the angular momentum per unit mass in the galaxy versus the log of the mass of the galaxy. This is the stellar component. And the rainbow thing here shows you what the bulged total stellar mass of the galaxy is. So these galaxies here that are bluish are essentially pure disk galaxies, and the redder things here are essentially pure spheroid galaxies. And you do see that there's a tendency for the intermediate types to fill in that gap. So these are difficult measurements to make, especially for the spheroids, because we don't know their orientation exactly, and a lot of the angular momentum is large radii. The rotation curves don't have a standard shape the way they do with disk galaxies and so on and so forth. So there is scatter in this. I think the scatter is mostly compatible with the uncertainties in making these measurements. But there's a general tendency you see for the bulbous galaxies to be high in this diagram and the diskless galaxies to be low in the diagram.
Should we take seriously that lower limit?
This one here?
No, you've drawn a red line suggesting that there are very few galaxies or no galaxies below that line.
This line here?
Yes.
Well, that's a little bit tricky. I mean, these galaxies have rotation has been detected in all the galaxies, if that's what you mean.
There are no non-rotating ellipticals.
Not in this sample, no. And it wasn't selected in any way that's related to that. Now, I mean, for the spheroid dominant galaxies, there is an uncertainty this way having to do with not knowing the exact orientation of the galaxy in space. So these are put at the median inclination angle, all of these galaxies here. So they could easily, the real value of this thing could be higher or lower. But there are none that are absolutely non-rotating in this particular sample. Rotation's been detected in all of them. So that suggests a way of thinking about galaxies. I mean, I think many people have thought about this, but not in this terms of this angular momentum way of thinking about things. These are two galaxies sitting next to each other in space. One happens to be almost a pure disk galaxy, and this happens to be a pure spheroid galaxy. And it won't surprise you that if you sort of imagine moving the two together, you would produce a kind of an intermediate type galaxy. And so it's interesting to ask, could you explain that previous diagram by assuming that disks all follow a scaling relation of their own and spheroids follow a scaling relation of their own, and then you just mix them in various combinations to span the space between these two? And the answer is that the data are consistent with that. So again, there are uncertainties, but to a first approximation, you can think of this angular momentum scaling relation as being essentially the superposition of two scaling relations, one for disks and one for spheroids, and then all the combinations of disk to bulge ratio between the two relations. Now I'm going to focus mainly on the disk part of that relation. For the best possible sample, this is a study of this relation of the log of the angular momentum per unit mass versus the mass of the galaxy, and for the disks alone. And what you see is that this relation is actually quite tight, and it has this slope has stayed the same for this relation for 40 years now. It's basically 0.6. And so that's the best relation now, this tight linear relation. But they are, disk galaxies are consistent with being on their own private scaling relation, and then the spheroids, at least approximately something below that. Then you mix the two together.
So you said there's a transition from the disk to the spheroidal. So then how do you identify the disk as a separate population? Is it like the number is it obvious that have one disk population, easy to identify?
Well, the disk will have a young population of stars and gas in it, and so you can measure the rotation velocity of that separate from the spheroid. The spheroid's the hard part because you have to measure that with absorption lines. But the disk is relatively easy to do, even when there's a spheroid there. Okay, so I've shown you some relations that are power laws that galaxies obey, but not everything about galaxies is power law-like. And here's an important example of one that's not. This is the mass spectrum of galaxies. So the luminosity function of galaxies, but then converted using appropriate mass to light ratios into the mass function, sometimes called the stellar mass function of galaxies. A little bit confusing nomenclature, but that's the way it's turned out. And for comparison, this is the mass function of dark matter halos in a CDM-type universe. Okay, and it has a roughly power law shape with a slope of about -2. And if you now ask, if I were to match up galaxies with dark matter halos in a one-to-one monotonic way, you can see from the way these diverge from each other at high and low masses that would give you a ratio of mass in stars to mass in dark matter for galaxies that has this characteristic inverted U shape, with a peak here at a mass of about 10 to the 12 solar masses, about the mass of the Milky Way. So, and if you plot just the mass of the stars against the mass of the halo, that's that. But if you do the ratio, it's this. And so this is the so-called stellar to halo mass ratio, and it's come to assume a very prominent role in this field. This is one of the targets, in fact, that the simulations often try to match, is this function here. This is regarded as sort of a key property of galaxies, and it's just a reflection of the fact that the mass function of the galaxies is not a power law, whereas the mass function of the halos is. Now, what's the explanation for this? Well, the most likely explanation, at least at low masses, is that this is a result of feedback driven by young stars. And so as you go to lower mass halos, the escape speed from the halos goes down and down and down, and it becomes easier to eject material from the system. And that then becomes increasingly difficult as you go to higher masses. And that gives you a trend like that. That's the belief in the field. And I think that's actually quite plausible. The belief in the field also is that this is the result of AGN feedback, which takes over at a mass like this and becomes the dominant feedback mechanism. And that becomes stronger and stronger the more massive the galaxy gets, the more powerful. And now the details of how that works are very, very sketchy. And I have to say, I don't think it's actually, beyond question that that is the actual mechanism. You can think of others like the inefficient cooling of the gas in a galactic halo. Once you get up to very high masses, that's another effect that may contribute to this as well. But anyway, that's the standard story in the field, is stellar feedback here, AGN feedback here.
But didn't you make a persuasive case at lunch on Tuesday that we shouldn't believe the simulation results for the halo mass function below about 10 to the 10th solar masses?
No, what I actually, let me just restate it. I made the case that you can't trust what's happening to the stellar component, the baryons in a halo, when the halo consists of very massive individual dark matter particles. Okay, you need about 1 million of those. But this result here comes from many, many simulations, pure dark matter simulations. You can run a simulation with no baryons whatsoever in it, and you always get something like this. So, and there's a theory for how that works, and this is pretty solid now. If you were to put stars in one of these halos and watch what happened, I would say down here in the simulations with low dark matter resolution, it would puff up the stellar system. But I think this mass function here is quite solid all the way down.
Sorry, it seems the break of the first LED panel is different from the break in the second panel. Is that true? Here it's like 10 to the 11, and then on the right panel is 10 to the 12.
Yeah, but you have to look across that way. I mean, this is stellar mass here. This is halo mass here.
Oh, okay.
Okay, halo mass here, stellar mass here, stellar mass there, and that break there is that break there.
Oh,
Okay. All right. So in a universe like CDM cosmology, the main mass component is not what we're seeing, of course, the luminous parts of galaxies, but it's the dark matter. And so it makes sense in trying to interpret those relations that we also look at the corresponding relations for the dark halos of galaxies. And because the dark matter is a dominant mass component, there's a good bet that those exert a strong influence, the properties of the halos exert a strong influence on the galaxy properties. Now, the relations for dark matter in these cosmologies, CDM-type cosmologies, is now very well understood. This comes from, pure dark matter simulations that go back 20, 30, maybe even more years than that. And these are very solid results. The scaling relations that come out are very clear. We understand them. There's a theory for them. There's simulations for them. And here's what they show. That the mass of the halo, and this is a region of space defined to be where the mass enclosed is 200 times the background density, or some number times the background density. If you do that and use the virial theorem, then it's easy to get this little scaling relation here. If you run the cosmologies and they satisfy the constraints from the microwave background, you can get the coefficient as well. But the scaling with velocity, the so-called virial velocity, the halo, versus the mass of the halo, is essentially a consequence of the definition of a halo being defined as something that's a fixed multiple of the background density. That's the definition. That corresponds roughly to where the halo is turning around. Stuff that's outside of that is still going on out. Stuff that's inside of that's turning around and virializing. And that gives you this relation here. Mass of the halo goes as velocity, the rotation, circular velocity of the halo to the 3 power. Now you can also look at the angular momentum. The angular momentum comes from the fact that the different halos, you know, exert tidal torques on each other. Jim Peebles worked this out, and we understand this quite well as well. The tidal torques cause all the halos to spin a little bit. It's not a lot. It's typically about as tenth as much as they could if they were going at the breakup speed. But the particular scaling that comes out of this is that the halo angular momentum goes as the 2/3 power of the mass of the halo. And that's equivalent to the statement that the so-called spin parameter, the lambda parameter, is mass independent. Those are, and the fact that the halo is defined by a constant overdensity criterion. And then here's this mass of the halo, the number of halos of different mass going like m to the -2. So this is the kind of background arena in which galaxy formation takes place. And this is the dominant matter contribution here. The baryons are largely going along for the ride in these halos. And so it makes sense to, you know, to normalize the story in terms of these very well-known scaling relations for the dark matter. And one of the ways that's done now frequently is in terms of these two ratios, Fm and Fj. So Fm is the ratio of the stellar matter in a halo divided by the dark matter in the halo. That's also called the stellar to halo mass ratio. And then there's an analogous ratio here for the angular momentum. That's the angular momentum in the stellar component divided by the angular momentum in the halo component. Okay, and if nothing else happened, if the baryons just followed the dark matter, then these ratios would all be this, they would be constant, they would be independent of mass. And the question is, what do they really look like? But so we can take those scaling relations for the stellar components of galaxies and normalize them. They already look quite similar to these. So it makes sense to normalize them this way and see what's left over in terms of Fm and Fj parameters. Anyway, that's a standard way of doing it. You don't have to do it that way. You could do it just directly from comparing with the known relations here, but this is the way it is. Okay, there are two simple consequences that come directly from this. There's a V versus M scaling relation for the stellar components of galaxies. There's a V versus M scaling relation for the dark matter components of galaxies. They're both power laws. So we can write down this ratio Fm, which is the mass in stars divided by the mass in halos. That has also to be, if I take two power laws and divide them by each other, I'm going to get another power law. In this particular one, if I take the measured slope from Tully-Fisher and put that in here, that says that the stellar halo mass ratio, this Fm, the ratio of stars to dark matter in galaxies, has to be a power law, no feature in it, with an index of 0.4. Okay, so that's in direct contradiction. It's in direct contradiction with what I told you here, which is that this ratio looks like an upside down U. But if the scaling relations are true, that can't be true. Oops, sorry, I'm going the wrong way. If the scaling relations are true, and they are, then this has to go like that. So there's a paradox here that has to be resolved.
So that data was the observed Tully-Fisher,
Mhm.
which is cool. Okay.
Yeah. Okay, so that's the first consequence. So that's something we're gonna have to deal with here, and we will in just a minute. Now, the other thing is from the there's a J versus M relation for the galaxies. There's a J versus M relation for the halos. They're both power laws. So we can divide by one by the other, and that tells us that these two so-called retention factors, Fj and Fm, the ratio of these two, one divided by 2/3 power of the other, that goes like m star to the alpha. Alpha is the slope, the observed slope of the angular momentum relation, minus 2/3. But the observed value here of alpha is 0.6, which is very close to 2/3. So that means that basically this ratio here has to be almost constant. Not exactly, but almost constant. So that means these two functions have to have almost the same shape. Now, this is a slightly muted version of this one, 2/3. But if one of these has a bend, the other has to have a bend. There's no other option. It's just math. Okay, so if one has a bend, they both have to have a bend.
I'm a little bit confused about the first one, though. The relations you showed us before were for stellar mass over dark matter.
Yes.
And now you're talking about total baryonic mass. You said that if the baryons follow the dark matter. So what about the conversion of baryons into stars?
Well, I'm not getting into that issue yet. I'm just saying there's an observed relation between the mass of stars in the galaxy and how fast the galaxy rotates. That's the Tully-Fisher relation. It has a slope beta. There's another relation between the mass of a halo and the circular velocity in that halo, and that's a power law. So the ratio of the two also has to be a power law. That's what the ratio is right there. There's no bend in either one of those. There's no bend in the relationship between the circular velocity of a halo and its mass. That's a power law. There's no bend in the relation between in the Tully-Fisher relation, the observed relation between the stars and the velocity at which they rotate in the galaxy.
I mean, strictly speaking, Tully-Fisher is just for spirals and, the stellar mass, halo mass, that transition is really for the most massive spirals anyway. Although, I mean, you can talk about Faber-Jackson, which is kind of another version of.
Right. I'm skipping over Faber-Jackson. There's a similar treatment of that. There's an extra complexity there, which I'll talk about later. We'll get to that, but I'm trying to keep it simple here. It's much simpler for things going around on circular orbits. And so that's what I'm talking about here. So what I'm trying to say is that there's a contradiction between stuffing galaxies from this function into this function and just looking at these power law relations as they come out of the dark matter simulations and as they come out of the Tully-Fisher relation. One says that this relationship should be a power law, that it should not have a bend. This argument says it should have a bend. So what's going on here? Okay, anything else? Okay.
You're assuming that the velocity that's measured in the Tully-Fisher relation is the same as the virial velocity dark matter halo.
Right. So that's that statement there. And so that's assumed in here. We've tested for that, and that's correct. So I'm giving you the simplified version. That just trust me that when we relax that assumption and do the whole thing again, you still get the same problem. You get back the fact that that is a true statement. Okay, so we got interested. We wanted to think about it. There's something going on here, and figuring this out is going to lead to some kind of insight. It's going to lead to something interesting. So just bear with me. We got interested in this, and and this is one of the projects we did. Now, there are data on the motions of globular clusters out to large distances from elliptical galaxies. So basically, what we decided was we needed to try and understand directly what the relationship was dynamically between the masses of galaxies and the masses of their dark matter halos. If we could do that, we could answer, we could get at this certainly. So there are a couple of projects here to do this. One is for early type galaxies here, and that's a sample of 25 largish early type galaxies, spheroid dominated galaxies, and the globular clusters that surround them. And from the motions of those globular clusters, we can in principle learn about the mass distribution, not in principle, but in practice, we can learn about the mass distribution in this combined system of the stellar body of the galaxy and its dark matter halo. Now, this would be the mass of the halo would be indeterminate if we didn't make some other assumption prior on that. And what we've adopted is, if we assume though that the halos are drawn from a population of lambda CDM type halos, the kind that grow naturally in a universe with lambda CDM initial conditions, then they have these so-called NFW profiles. We know what the density of the halo is as a function of radius, and we know a relationship between how concentrated the halo is and the mass. If you adopt this as priors, you can actually estimate that you do get a definite answer for the mass of the halo with from this globular cluster data extending out about 10 times as far out as the sort of effective radius of the galaxy.
You also don't know about the radial anisotropy of the.
Well, that's fitted for, and that's basically here again. So you can fit for all of these things simultaneously. There's enough information, we have enough clusters to do this. You can get basically the circular velocity of the two combined components as a function of radius. You can get the anisotropy of the globular cluster system.
So you're writing down some distribution function and fitting the parameters.
Yeah, it's a very flexible distribution function.
Is there good reason to think that globular clusters should be following sort of equilibrium modeling procedure? If they just fell in, they were accreted.
Yeah, I mean,
time is so long.
Sorry?
The dynamical time is so long. That should they really be following some FOB?
Yeah, I mean, they may be slightly out of equilibrium in the outer parts here, but people have done tests on that, doesn't make a big difference. Anyway, so this is a way to estimate the masses of all of the halos of the galaxies. As I said, this is an indeterminate problem unless you make some assumptions about the halo. And the ones that are made here is that we live in a universe that had lambda CDM initial conditions, and then that closes the problem. A problem that you couldn't solve before, you can now solve. And there are uncertainties on these estimates. Here's the probability distribution for the and this is with marginalizing over some of these other quantities here. And here's the one for the mass here. So so we can estimate the total dark matter mass of these galaxies. We observe the luminosity in the galaxies. We know roughly what we fit for the mass to light ratio of the luminous body. So we're also estimating with the same data the mass of the stellar component of the galaxy. We can take the ratio of the two and plot that. And so that looks like that. These are these pink points here. So this is the mass in stars plotted against the mass in stars divided by the mass in the halo plotted against the mass in stars. These are for some disk galaxies, which I'll come to in a minute. And here are the ones for these massive elliptical galaxies, where we've estimated the total mass of the galaxies. And they do follow this abundance matching curve here. Okay, the disk galaxies here, and they're easier to do, but the population gets very thin up here. There's a hint maybe that there's a difference up at the top here. But the point I want to make here is that the positions of the elliptical galaxies in this kind of diagram here, this stellar mass halo mass diagram, is consistent with the abundance matching that people do in this field all the time. And so, this is sitting right on the curve where you would expect them to be if you did this abundance matching. The abundance matching is not a mystery. I mean, think of it this way. You have a simulation, you have a population of galaxies, and you go to the most massive one, halo in the simulation, the most massive galaxy in your sample, and you say, put those inside each other and you do the number 2 and depth 3 and so on and so on and so forth. You make that kind of matching. People do that. You have to correct for sample size and things like that. But people do that all the time. And that gives you this result here. And these estimates of the dark matter halo mass are consistent with that. So check that box. Now, there's a hint in this diagram. This is from a sample of nearby galaxies. This is the same sample that led to that Tully-Fisher relation that I showed earlier, the modern Tully-Fisher relation. That's basically comes from this same sample here. And there's a hint that maybe they're not doing the same thing as the elliptical galaxies. So we got interested to see if we could clean that up a bit. It turned out that one of my colleagues at STSCI got very interested in studying the population of the most massive possible spiral galaxies. I'm not even sure why he was interested in that, but anyway, he scoured the Sloan survey, he scoured 2MASS and so on and so forth, and came up with the largest, brightest, most massive spiral galaxies he could find out to redshifts of about 0.3. And these are galaxies that have stellar masses more than about 10 to the 11 solar masses, almost all the way up to 10 to the 12. So, and they have rotation velocities that go up, most of them are above 300 and some go all the way up to 500 kilometers a second. They're really monster things. They have sizes that are tens of kiloparsecs. I think one of them is 80 kiloparsecs or so is its characteristic size. So we decided that we'd like to do something like halo mass estimates for this population of very massive spiral galaxies to see what the relation at very high masses is between these two things here. I mean, that's interesting in a number of ways, because I think, at some point near there, we just start running out of galaxies. The universe stops making galaxies at that size. Instead, it makes things like clusters of galaxies. You never see, say, a galaxy that's as big as with a dark matter halo as big as the Coma cluster. Why is that? There's something that stops making galaxies above a certain size. And so it's interesting to ask whether what happens to these scaling relations up at that. Maybe there's going to be a hint. If you found a break, there was a hint of a break actually in some of the relations. We wanted to see if we could verify that or refute that. So we did a similar study on these massive spiral galaxies that overlap. We also plotted the scaling relations for these galaxies. We have about 50 of them where we have the H alpha measurements, and then we have about 15 of them where we have the 21 centimeter extended rotation curve. So we can plot the scaling relations up to the highest possible masses. And here's the Tully-Fisher relation. Here, the stellar mass versus the rotation velocity in the flat part of the rotation curve. And you see these high mass galaxies sit on the same relation. And then here's the one for angular momentum. Sits pretty much on the same relation, slope again 0.6. There's no really significant bend here. There's a little more scatter in this one than the other one. And again, the same story in terms of scaling relations. So
it's like there, these other comparisons with earlier work, what was different about the high mass population they had?
Well, this is us. This is just a different, this is the H alpha measurements, which you can do to much larger redshifts.
And so those light blue ones were 21 centimeter or what?
These are 21 centimeter. This is a very local sample here.
But theirs goes up above 10 to the 11 also.
A few of them, yeah, but it peters out here. This is the same sample. The blue ones there are the same ones as here. So there are a few up there, and there's a hint that this relation continues up. So we wanted to check that. So we did two projects. One with these H alpha measurements, which can be done out to redshift of 3, then one with the extended 21 centimeter rotation curves, which because of radio interference can only be done out to redshifts of about 0.05. So it's a smaller volume. We don't go quite as high up in mass. But anyway, they all follow the same relations here as we can see. So there's no way to get out of this in terms of abandon this relation. And again, following fairly standard procedures for the ones with these extended rotation curves, we can also estimate the total halo masses with the same priors that we made for the early type galaxies. So that is that they have NFW profiles. They follow the same CM concentration mass relation that dark matter halos in a lambda CDM universe have. And we can do the same kind of fitting then for the mass of the halos here. And then we can see what we get here. And this is the answer. So again, this is the ratio of the mass of stars in the galaxy to the mass in the halo versus the mass of stars. And this is the abundance matching result. And this is where the galaxies sit here. They sit well above that. And this slope here is about 0.4. That's the one that we said you had to get if the Tully-Fisher relation and the angular momentum relationships were power laws to the observed slopes that they have. It's a prediction that this should come out this way, that it should not do this, and it doesn't do that. It does actually stay on a power law there. So the disk-dominated galaxies are on a power law. They have masses much lower than the ellipticals. The ellipticals, remember I showed you in the other diagram, they track this here. And at these highest masses, above 10 to the 11 solar masses, there's a big difference in the halos that elliptical galaxies live in and spiral galaxies live in. The ellipticals live in halos that are about 10 times heavier than the spirals at the same stellar mass. It's a really, really big effect. Now, there are not a lot of galaxies up here, but those that are up there have very, very different properties.
The stellar masses are gotten from stellar light.
It's
They're high ones. Red ones are very rare and far away. Is there a possibility that the mass to light ratio is incorrect?
not at the level that would matter. I mean, look, there are error bars here and so forth. So yes, you can make errors in the mass to light ratios, maybe 50%, 30% or something like that. I mean, these are infrared luminosities, so they're not very much affected by dust, and they're not very much affected by the current star formation rate. You're almost measuring mass directly. So those should be pretty reliable. Maybe 20%, 30% errors. But look at this is a big effect.
I just wonder, maybe you're looking at light that is blue at shift 2.
Well, these are less than 0.05. These are,
Oh.
yeah, so these are, you know, in our epic here, there's no.
Is the horizontal dashed line the cosmic ratio?
Yes, yes, and this is good. Thank you. I need to point that out. So we're getting to the point now where at least some of these galaxies are consistent with having no CGM within the errors. So the galaxies down here are completely, this is presumably galaxies material that was once inside the galactic halo. It may have escaped and be gone from now. But anyway, this was material that in principle was available to make stars, but didn't. And there's less and less and less of that as you go up here. And you get to the point here where the stars you see in the galaxy are consistent with a large fraction, maybe even all of what's there in terms of baryons. This is their allocation of baryons. It's getting to the point where, you know, there's still, it could be a factor, they could still have half, or, I mean, even down here in some of these cases, even a tenth, but the typical number is getting to be of order unity here. So that's another surprise from this work. But again, it has to be this way if these relations, if the fact that the Tully-Fisher relation is a power law requires this. There's no way around it. I mean, in a sense, this is confirming what has to be true mathematically.
And do we have physical intuition of why the Tully-Fisher is like that? It's a power law.
Well,
Because it like at some time it just use up all the barrier.
yeah. So the efficiency of star formation with the feedback effects and so on and so forth are becoming, they're weak down here. I'm sorry, they're strong here. That's presumably the reason that basically the amount of baryons that you can see is so far down here. Presumably the escape speed is very low in these halos, so the material's blown out and stops not available to form stars. So that's why these things are down here. As you go up and up and up, your ability to do that, because the deeper potential well goes down. And so what we're seeing is the efficiency, the overall global efficiency of star formation in these galaxies is going up and becoming quite high, almost as high as it could be. So now what does that do? And here's the other thing that is interesting about this. Remember, I told you that the standard explanation for this upside down U shape of this curve here is that this is stellar feedback here, and this is AGN feedback here. But just think about it for a minute. The black holes responsible for AGN feedback are fairly tightly correlated with the spheroids of galaxies. And guess what? These galaxies don't have spheroids. So in a way, you could have expected this from that kind of argument as well. Whereas, the elliptical galaxies here are all spheroids. They all have really massive black holes. So I think there's a slide here that shows me. So there are a number of interesting things that come out of this. So yeah, here it is. This is from a review by Cormany and Ho. Scott's the expert on this here. But the point that's made in this review article is that the black hole mass is very tightly correlated with the spheroid stellar mass and not correlated at all with the disk. This is the mass in the disk here. I'm sorry, you can't see it very well, but this is the black hole mass. This is the disk mass, black hole mass, bulge mass. So here there's a tight correlation. There's no correlation. And, if this really is the result of AGN feedback, then it's not surprising not much of that happened to these galaxies, and they should sit up there, and they do.
What's the fraction of galaxies that are spirals and ellipticals as you go up in the mass in 10 above 10?
Okay, that's a very good point. The population of spirals peaks here. So the fraction of spirals is high here, low here, and low here. And that explains why when people have done this empirical abundance matching, they find this because the ellipticals dominate the upper end of these samples when they do the abundance matching without regard to morphological type. Effectively, they're looking at the curve for the elliptical galaxies, which, as we saw, they fell on the curve just like they're supposed to. So there's a story here that I think all hangs together. And then down here, it's also mostly dwarf spheroid galaxies.
Your very massive disk galaxies occupy a very small fraction of the halo. So your assumption that they're typical halos is probably wrong. They're statistical outliers in some sense. And so the concentration relations, all of those things, can't assume that they sit on the mean. Right?
Well, we did. I'm sorry. It's possible that there are issues like that would be hard to disentangle. So the simplest thing is just to assume that these are in the typical halos. It could be that somehow a halo with a different concentration was more likely to make an elliptical versus spiral.
And especially if you have some very low concentration to result in something that isn't very centrally concentrated.
Yeah.
It makes a big disk, right?
It's not a very strong, the concentration mass relations are very weak. Very weak. I would be shocked, actually, if it really made the kind of difference you're talking about. You probably would be too, I think. It's a very weak effect. Anyway, there's nothing we can do about it. You'd have to run the hydro sims.
Well, we'll probably need to look at the statistics of the concentration. I mean, the concentration mass is not a very strong relationship, but it's a statistical question. I mean, are these things rare enough that they could be out on well, 3 sigma things on?
No, they're
some
not.
galaxy
They're rare because the number of galaxies is going down with mass. But at a given mass, there's no reason to think they're any rarer than anything else. Yeah, I mean, they're rare because the population of galaxies is going down this way. Okay, so the
Nearly everything
rareness,
at that mass is an elliptical.
the rareness is along this axis. It's not necessarily, it could be, there could be some of that going along this axis. You know, there's nothing we can do about that, but, you know, I mean, the way to get at that would be maybe with these hydrosims to see, you know, for the most massive galaxies, do they form in high concentration or low concentration halos? And maybe we should have a look at that, but.
But this, I mean, you were just using H1 rotation curves anyway, right? So-
Yeah. Yeah, but in order to get a finite answer, you know, as you know.
Concentration doesn't affect the mass at that, I mean, it's just the NFW assumption, right? Basically.
Right, but I think what Jim is saying is that if not all the halos have the same.
That's the break.
Yeah, so you're so far past the thing.
Same concentration. So if you have some very weak thing, I guess the real question is, at a given halo mass,
Yeah.
what is the fraction of disk galaxies?
Oh, what is the fraction of disk given halo mass?
Yeah, given halo mass.
We have plotted that. A given halo mass. Well, if you plot these against halo mass, of course, the ellipticals extend way out here. They go to much higher masses and so. But I don't
If you have a
think.
10 to the 13 solar mass halo, what fraction of the galaxies in those halos are spirals? And if it's very small, then they're statistical outliers in some sense.
Well, it's.
It might not be small.
Yeah, we should talk about, I mean, I think,
Yeah.
yeah, it's an interesting point. I mean, we know we're making this assumption of ignoring it.
Another question,
Yeah.
which is, I mean, you have rotation curves, H1 rotation curves out to very large distance for these galaxies. So if they follow an NFW over that very large range, then it doesn't, you know, if it's out beyond the break anyway. then-
But not all galaxies follow NFW. I mean, there's statistical outliers in
But
the
that's-
shapes as well.
That's-
And
I
that
think
may
that's
be the
just-
thing you're looking at.
Yeah, I think that's
Yeah.
just a question though, whether they look like they follow an NFW.
Well, the thing is, we don't actually go out to a large fraction of the virial radius, which is
Of
what you'd
course.
really need to
Of
do.
course.
We track it out. Here's an example. This is a typical example here. You know, the rotation curve is affected by the luminous part of the galaxy and then the darkness and so forth. We just assume that this, you know, has an NFW thing with these properties, and that is what closes, that's what gives us a finite mass. We wouldn't get a finite mass if we didn't do that. You know, it could be infinite. It went on indefinitely.
So Michael, have any of these giant spirals AGNs?
Well, we're looking at that. There are some X-ray observations. We're starting to look at that. As far as I can tell, not a lot, no.
Without an AGN, you don't have a black hole, but if you have an AGN,
Yeah.
then you might wonder why it was not employed. You know,
Well, then you get into duty cycle issues and that sort of thing. But the general point I'm making is that these are disk-dominated galaxies. They don't have spheroids, so on average, it's unlikely that they have lots of massive black holes in them because they don't have massive.
M101 doesn't have a disk, it has a black hole.
Yeah.
It looks like it.
I know, and the Milky Way has a very small black hole, so there's a scatter and all of that. But anyway, the Cormandy, the experts, I mean, maybe Scott should weigh in on this, but this is the Cormandy thing, and I don't know how much of this he's edited. But this is the claimed relation between the black hole mass and the bulge mass. I'm just making a very basic point that there ought to be more AGN feedback in galaxies that have huge spheroids compared to the ones that have very little or no spheroids. And that's consistent with the story. It's not a proof, but at least it's consistent. And if you really believe that the story about AGN feedback causing the turnover in the stellar mass halo mass relation, you should have expected this result.
Your absorption line systems show small circumgalactic halos around these giant spirals.
We haven't studied them in that detail. A lot of them are pretty far away, and
Well, that's all right for an absorption line system of a background quasar.
yeah, I mean, yes, that might be a thing we should do in the future, but it's a big effort to do those searches, and usually you don't find anything, and so we'll get to it, but not right away.
So, I mean, I think usually those stellar mass, halo mass matching is based on a central galaxy.
Yeah,
And your spirals, this sample, are they also central galaxies?
well, in a way, we're treating them as central galaxies. We've kind of probably they're central, we pick the galaxy and we're going out and see, and that's all we can do is
But the
go.
physical environment might also be a factor.
Could be.
Wrap up the
Oh, okay, so let me just say, we can calculate we can calculate this ratio FJ, the ratio of angular momentum per unit mass in the stellar component to angular momentum in the halo, and that has, for these spiral galaxies, this very flat relation here, the ratio is about 1. It's essentially independent of, or almost independent of galaxy mass. And this is of interest because this is the assumption that gets made based on tidal torque theory. We expect the baryons in the dark halos to get the same angular momentum per unit mass. And then if that's not too messed up by intervening processes, then you might expect the disk in the halo to have roughly the same angular momentum. This, though, is an empirical determination of this average ratio. On average, the angular momentum per unit mass in the disk is the same as the angular momentum per unit mass in the halo. It's within, 20 or 30%. So that's another nice result. And that comes about just because the relationship between angular momentum and mass in the stars of galaxies is parallel to the relation for the one in dark halos. So the ratio of those two has to be independent of that. And that's essentially what this is saying here. The fact that they have nearly the same angular momentum per unit mass means you can calculate the ratio of their sizes to the sizes of the halos that they live in. Once I tell you that the angular momentum per unit mass is similar, FJ is similar, so the disk angular momentum is similar to the halo angular momentum. This is the halo angular momentum here. It's basically lambda times the circular velocity times the radius of the halo. This goes back to work I did many years ago with George Estathiou. And the disk angular momentum is just per unit mass is just this twice the circular velocity times the size of the disk. You take the ratio 1 to the other, you put in the average value of lambda, that's 0.035. And that means that basically the sizes of the disk are 3% of the size of the dark matter halos, and that's roughly independent of mass. And there's no theoretical assumption here. I mean, there's been some controversy about whether galaxies should have the same angular momentum per unit mass as their halos. There are many reasons why they should gain some or lose some and that sort of thing. None of that applies here. This is just a completely empirical. There are two relations. They're one for dark matter, one for disk galaxies. They're parallel to each other. Divide by one by the other, you get this ratio, and that tells you that the sizes have to be in this ratio as well. So whether you like it or not, this is the correct formula, independent of what you think the reason is for the galaxies keeping the angular momentum that they had from tidal torque. Now, can I just take a few more minutes?
Yeah.
Okay,
2 minutes.
this is real quick. I made some nasty remarks about the simulations on Tuesday, and so you should keep those in mind. But these simulations are so seductive that it's impossible, even for someone who doesn't trust them completely, not to look at them. So I just want to show you what comes out of these simulations. So here are a bunch of this is the IllustrisTNG. This is a galaxy here. Now, I want you to think about these scaling relations. They're pretty tight. They look very stately. I mean, when we plot them, we're not talking about the activity of a real galaxy and what will be going on inside it. This might give you some indication of that. So I want you to think about those scaling relations while you look at these movies. I'm going to show you 3 movies. This is a galaxy here. It's starting at a redshift of 4. This is all pretty quick. Redshift of 4. So here's the gas temperature, the gas pressure, the gas metallicity, gas density, the gas entropy, the cooling time. I'm not saying this is all right. This is, and the radial velocity of the gas. There are many issues that you can complain about these simulations, but the general sort of chaos that they portray, I think, is probably qualitatively correct. Okay, let me just leave it at that. Let me show you this movie. We're starting a redshift of 4. Just watch how crazy all this is. And then wonder about how you're going to end up with nice scaling relations at the end of this. So that's what's going on in the galaxy there. And now things are calming down. All right, let's go to the next one. So this is just a region of space here that's going to end up in the formation of a disk galaxy. And let's just watch the history of this thing. This is starting at a redshift of 2. This is a typical example in the Illustris simulation. So again, we're making a disk galaxy, starting at a redshift of 2, counting the redshift here, the stellar mass there, the star formation rate, specific star formation rate, and so on and so forth. So, you want to come to the lights here?
Galaxy not formed,
It's getting there, Jim. It's getting there.
but the Milky Way is pretty well formed by a redshift of 1.
Well, I'm not saying that this is the Milky Way, but it's I think it's a Milky Way-like mass here. Actually, this is nearer the mass of the galaxies. This is so this is okay. Now this thing, believe it or not, is going to end up on one of these scaling relations. That's the miracle here that I want you to think about.
Did it ever end up as a flat disk?
Watch, it's coming. So again, I don't think you should take this as gospel.
Have you an image of it there, John?
Probably. Now here's early, in the interest of time, let me just go. Here's an early type galaxy. Now this is going to form an elliptical or spheroid or something. Starting a redshift of 6. And I think, this is one example. Any other galaxy you picked in the simulation would have almost equally complex history. That's the point I'm trying to get across. Is you have these nice tight scaling relations. Somehow galaxies know that they're going to end up on these things, even though this is how they spend their life. How does that happen?
Maybe it's not quite lambda CDM.
Simulation.
At this point, you can't even tell where the galaxy is.
Well-developed early type galaxy seen at redshift 1.5.
Yeah, in some cases, yeah.
This one would not look like much.
This one wouldn't, but some of its constituents might. Okay, now it's having a fit here. I think it's even going to look like a spiral for a while, and then it's going to turn back into an elliptical.
The lack of blue light implies there's the simulation, there's little star formation taking place, or just seeming.
I'm not sure what the colors mean. I think basically this is just the projected stellar density, independent of how old the stars are. I don't think it takes account of the age of the stars. So this is not what you would expect to see in a talk. It's just the projected density, I think, of star mass, I think. Yes. Okay, so, I mean, maybe these simulations are right, maybe they're not, but if they are right, then, you know, so that just, if I could just have a light, just one quick minute. The galaxies in these simulations do, I just want to say real quick, we've checked all the various relations. They're subject to the caveats that I talked about. They do sit on these relations. So that crazy history of those two galaxies and all the other ones in the big box as well end up on scaling relations like the ones I showed you from observations. So I think that's an interesting point. So here are some conclusions. Galaxies obey power law scaling. This is the what I hope to take away from this. There's a nice set of conclusions here from what we've just been through. Galaxies obey power law scaling relations in mass versus rotation velocity, circular velocity, and in angular momentum versus mass over this full range in mass. There are no bends as far as we can see to the upper end of the mass of the sequence of galaxies and down to the lower end. No features. Nice contrast. At fixed mass, the positions of galaxies in the J-M diagram corresponds with their morphology, correlates with their morphology. I submit to you that that's a perfectly good way of thinking about different galaxies. It's a more physically way of thinking about the Hubble sequence, I think, than SA, B, C, and whatnot. And it's consistent with basically standardized disks and standardized spheroids just glued together. The stellar mass halo mass relations of massive early type galaxies and late type galaxies diverge. The early type galaxies have FM, fraction of mass in stars, much less than the baryon mass, while the LTGs, the late type galaxies, have masses similar to the baryon fraction for the universe as a whole. The possible reason for that is AGNs. Of course, mergers potentially play a role as well in terms of directing flows into the AGN and promoting more AGN feedback. That people are working on that sort of thing, but the data here are sort of consistent with that story, at least qualitatively. The early type galaxies have a characteristic mass scale at the peak of the star formation. The stellar mass halo mass relation at about the mass of the Milky Way. Late type galaxies, disdominated galaxies are basically scale free. You've seen one, you've seen them all. Just scale them up and down a bit. They're not perfectly self-similar because the ratio of mass in them is a weak function. So if I told you what FM was for a spiral galaxy, you could tell me roughly what its mass was, but there are no features in any of these relations. So in that sense, I would call them scale-free. Late type galaxies have approximately the same angular momentum per unit mass as their halos, and so their sizes are given by this relation here, disk 3% of the halo size. And then the scaling relations actually that come out of the simulations are pretty close to the ones we observe, at least at the factor of 2 level. And, if you were at lunch on Tuesday, you heard me making comments about how these relations shouldn't be trusted at the very low masses. The high mass is a little bit better, but anyway, for what it's worth, something like these observed relations are coming out of the simulations. And I think that's my story. Thank you. Thank you.
Well, up past the hour, we've had a lot of discussion, so I suggest we carry this on at lunch. Mike will be here till the end of next week, is that right?
Yep.
And there are also spots available for dinner if anybody would like to sign up. So, thank you.